can you see the screen now?
Yes, sure.
Okay. Okay, guys, so we are done with the network layer about 2 weeks ago, if you guys remember. Today's we're gonna move on to the next chapter, which is gonna be link layer. This is the fourth layer from the top. So, so let's see what are the main goals in this chapter. First of all, we are gonna try to understand the principles behind these link layer services. What are the services that we provide at this layer are as follows. So the first function is error detection and correction. So because when we transmit the bits, these bits can be flipped. So we need to detect these bit errors as well as we need to correct them. Another important feature of this layer is a multiple access, because when you talk about a network, you have multiple users, multiple mobile devices, right? And multiple hosts. So you need to provide a fair services all these devices simultaneously, because they may use the sharing channel. And another issue in this layer is try to address a new type of address, which we call MAC address, and it's different than the IP address. So how do we handle this link layer addressing? We're gonna learn this. And then we will provide some local area networks, which are Ethernet, virtual local area networks, Wi-Fi, and so on. So let's look at the outline. We are going to cover the following topics. We will provide some introductory information. What are the services that we provide in this layer? And then we will move to the error detection and correction mechanisms. More importantly, the multiple access protocols and the local area networks. Some main feature of these local area networks, including addressing, ARP protocol, address resolution protocol, Ethernet switches, and VLANs. And then we're gonna done today. Okay, so let's remember that our network, we have such networks. And in this network, we have the hosts and routers, if you guys remember. These are the host, the end user, and these are the routers. So in the literature of a network, we call these host and routers as a nodes. All of them are called as a nodes. And we need to communicate between nodes. So that's why we need that links. It's a communication channel that provide a communication path is called links. So we have two main entities, nodes, and the links that connect these nodes. These links can be in different form. For instance, it can be a wired links, such as cable, copper cable or fiber optic cables. Or these links can be a wireless, such as Wi-Fi and 3G, 4G, LTE, and so on. And we, of course, can have some local area networks. So at each layer, we have a different types of packet. At this layer, we call this packet as a frame. At the network layer, if you guys remember, we have the datagram. So when we push this datagram to down this link layer, we need to encapsulate. So we encapsulate datagram and we add the preamble or header, and then we call this as a frame. So at the link layer, the network packet is called frame. In summary, so this layer, data link layer, is responsible for transferring the datagram from one node to the physically adjacent node over a link. So the main job of this layer is try to move or transfer the datagram packet from one and to adjacent, physically close node over a link. Okay, let's look at this transfer of the frame, let's call it frame or datagram, how this is achieved at this layer or the network layer as well. You know, the datagram can be transferred by different link protocols over different links. So when you talk to, let's say, your mother or your father over an internet, this connection goes through different, it may goes to different links in practice. So first of all, you're at home and you are connected through the Wi-Fi links. Then from Wi-Fi to in your apartment switch, it can be a Ethernet. And from your apartment to the your ISP service provider center, it can be fiber optics cable, and so on. So it's a mix of different links actually in practice. And each link protocol can provide different services. And this may be reliable or not reliable data transfer. So let's look at this transfer of datagram by giving an example. For instance, transportation analogy. Assume that you're planning to visit, you're in Istanbul and you want to visit the Namrud mountain at Adıyaman Kahta. So you need to plan your trip from Istanbul to Adıyaman and Nimrud mountain. So first of all, you need to have a car or taxi to take you from home to the Sabiha Gökçen airport. And then from the Sabiha Gökçen airport, and there should be a plane. So the plane is going to take you from Sabiha Gökçen airport to the Adıyaman airport. When you landed at this Adıyaman airport, you need to take a car or shuttle, whatever, taxi from Adıyaman airport to the Namrud mountain. So in this example, what we are trying to carry is the tourist. We are trying to carry tourists from Istanbul to the Namrud mountain. So this is equal to datagram in the network. And the transport segment in this case can be like a taxi, a airplane, shuttle, and so on. And this is equal to communication link in the network. The transportation mode is equal to link layer protocol. And the travel agent in this example that, you know, plan your trip from Istanbul to Adıyaman Nemrut'a, so is equal to the routing algorithm. So is the actually routing algorithm in the network that plan all these datagram transfer like a travel agent in practice. Any question? Okay, so after this introduction, now we are ready to talk about the services at this layer. So the first important job or function of this layer is called framing and link access. So as I mentioned, so we receive the datagram from the upper layer, which is the network layer. We receive this datagram from the network layer and we encapsulate into frame and add an header at the front and a trailer at the back. That's called framing. So we frame the datagram at this layer, encapsulate, and obtain the frame at this layer. And another main important function is called link access. So you have a base station or you have a Wi-Fi access point, and in such case the channel can be shared. If you have a shared medium, you need to provide that link access to your hosts, your mobile devices, and so on. So this is called link access. Um, And then I talk about the new kind of addressing at this layer, which is called MAC addresses. And this MAC addresses is used in frame headers so that we can identify the source and destination node. Note that this MAC address is of course different than from the IP address at the network layer. So we will talk about these MAC addresses later on. So another important services that is provided at this layer is reliable delivery between the adjacent nodes. And we learned how to do this already at chapter 3. And this is sometimes is used on the low bit error link. And because reliabilities depend on the links that you use in the, kind of wired links, reliability can be achieved easily, but when it comes to the wireless links, due to its nature, it can have some high error rates. So that's why it's really difficult to provide that reliability at the wireless links. That's why we provide both link level as well as the end-to-end reliability. So let's continue on services at this link layer. It provides a flow control between the adjacent sending as well as the receiving nodes. And it provides an error detection mechanism. You know, guys, that these bit errors caused by the signal attenuation and during the propagation of the signal in the environment, as well as the noise that is generated by the devices. So this may cause bit errors when you transmit this bit stream. So the job of the receiver is to detect this if there's an error. So if there's an error, we have different kind of mechanism to handle these errors, or let the sender knows. So we can ask or send this information to the sender so that it can retransmit or drop frame. And we have another mechanism which is called error correction. If you detect an error, another alternative solution is to correct this error. So in this method, the receiver identifies and corrects bit errors without resorting to retransmission. And another services that is provided by this layer is duplexing. So it can be half duplex and it can be full duplex. In the half duplex, the nodes at both sides can transmit, but not at the same time. One of them, can transmit, the other wait, and then the second one then can respond. But in the full duplex, both sides can simultaneously transmit and receive. Okay, guys, so these are the main services that are provided by the link layer. Okay, so one of the good question is, where do we implement this link layer in practice, in hardware? And the answer is in each and every host. So in each and every host, like a laptop or PC or mobile devices, smartphones, whatever. So this link layer is implemented in each and every host. So link layer implemented is by using the adapter or technically it's called network interface card, NIC, or on a chip. And this is sometimes called Ethernet card or 8.0.11 card, Ethernet chipset, and so on. So this NIC card is implementation of both link as well as the physical layer. And we attach these to the host system buses, as you see from here. We have the physical layer, we have the controller, and this is attached to the host system bus, which is connected to the CPU and as well as the memory. So this link layer, this NIC card, is combination of hardware, software, as well as the firmware. So as you see, this NIC card is so physical and link layer, as well as at the top we have the upper layer that are implemented at CPU. So in summary, we implement this link layer by using the NIC card, or sometimes we call it adapter. How these adapters communicate each other at different nodes. Assume that we have a sending host and then we have a receiving host. And we receive the datagram from the upper layer, from the network layer, and we encapsulate and we obtain the frame. And then from controller to the physical layer, then we transmit this over the link, wired or wireless links. At the receiving host, we receive this frame. We remove the header and trailer, and then pass the datagram to the upper layer at CPU side. Okay, guys, that was the introduction as well as the services that we provide at the link layer. Any questions so far? Okay, so now let's move on to the next mechanism, which is called error detection and correction. So error detection and correction, which we called EDC, and D is stand for the data protected by error checking, and this may include some header fields. First of all, this error detection, of course, is not 100% reliable. So it cannot, detect all the erroneous bits. Sometimes it may miss some of the errors, but rarely, okay? And this EDC field, error detection and correction field, it has a limited number of bits, but when you have if you have more bits, this yields to the better detection and correction. But of course, it's limited because if you increase the number of EDC bits, then you're going to eat from your data bits, which is going to reduce your bandwidth. How this mechanism works, at the sender side, we receive the datagram. We have the data D bits, and based on an algorithm, we calculate the EDC bits and we add to the EDC fields. And then along with the data bits, we transmit over the link. And this link, this channel can be bit error prone, right? So at the receiver side, we receive these bits, which is going to be D prime. According to an algorithm mechanism, we compute the EDC bits. If all the bits in the D prime okay, then we pass this to the upper layer. If they're not okay, then we detect the error and we trigger a mechanism if needed. to detect and to correct these bits. So one of the error detection, the simplest version of the error detection method is called parity checking. And this is split into two parts, is called even parity checking or odd parity checking. So, and in this case, you can use a single bit or multiple bits, two-dimensional bit parity. So the simplest version is called single bit parity. So that's why it can detect only a single bit errors. So let's look at an example. We have these D data bits, as you see, and then we have a one single parity bit. So this is example is for odd bit parity checking. How it works? So you first count the number of ones at the data bits. So let's count together. We have 1, 2, number of ones only. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is an odd number, so that's why you don't put any kind of another one, because it has to be odd. That's why we put a 0, so that we can keep it as a odd. Okay, let's look at the two-dimensional bit parity. Because two-dimensional, it has an additional feature that it can correct the single bit errors. Because in the single bit parity, we can tell that there's a bit errors, but we don't know which one is corrupted. But in this case, in two-dimensional, we can tell which exactly bits is corrupted. So let's look at this case. We have 1, 0, 1, 0, 1. Let's count the number of ones. 1, 2, 3. We have 3 ones. So we need to in this case, the example is the even parity checking. That's why we need to make an even number. So that's why we need to add 1. So it becomes 4, which is an even number. In the second line, we have 1, 2, 3, 4. So it's already 4 is an even number. That's why we put 0. In the third line, we have 1, 2, 3. It's an odd number. We need to make it even number. That's why we add 1. So it becomes 4, which is an even number. And then we do a column wise. Let's count it column wise. 1, 1, 1, 2. We have even numbers. That's why we put 0. In the second column wise, we have 1, 1. 1, 2 is even. That's why we put 0. In the third column, 1, 2, 3, it's odd. So we add 1. We make it even. Is 1, 1, 2. So is an even. That's why we put 0. In the last line, there's just 1, so it's an even, so we add a 1 so that we can make it even number. And assume that this is the perfect case, there's no errors. When we transmit these bits, assume that these bits with the red one is corrupted. So when we transmit it was bits 1, but when we receive it becomes 0, so which is an error. So as you see, I'm just going to focus on specifically to this. So in this second line, the number of ones is 1, 2, 3, right? Is an even number. Sorry, is an odd number, but this parity bit is 0. That's why we assume that there's an error in this bit stream, but we don't know which one. And then we, compute for all the column-wise and line-wise. Okay, I'm skipping the other steps. Focus on the second column. As you see, number of ones is 1, but the parity is 0. That means there's an error. So because of the intersection of this, it gives this specific bits that is corrupted. So we detect and find the erroneous bits using two-dimensional bit parity checking. Okay, that was the error detection and correction at the link layer. If you guys remember, we have another mechanism at the transport layer, which we call internet checksum, if you guys remember. And the main goal of this internet checksum was to detect errors in the transmitted packet, right? So how this was working, let's refresh our mind. At the sender side, we treat the segment contents as a sequence of 16-bit, and then we add them up by using the ones complement sum, if you guys remember. And then we obtain the checksum value into UDP. And then we send this along with the data. At the receiver side, we compute the checksum of the receive segment, and we compare with the checksum field value that we receive. If the computed and the received checksum value are equal, right, then there's no error. But if they're not equal, then we detect an error. So CRC is another kind of error detection mechanism, cyclic redundancy check, and it's more powerful than other detection coding, error detection coding, such as the parity checking. So in this case, we have the D, which represent the binary, data bits, and we have the bit generator, which is G. And the main objective in these CRCs, we are trying to choose an OR, which is CRC bits, such that according to this formula, mathematical formula, in an XOR formula basically. And then once we obtain the CRC, we add these CRC bits to the frame, and then we send along with the data to the receiver. And this is very popular error detection coding that is used in many technologies, such as Ethernet, Wi-Fi, ATM, and so on. And this can detect all the burst errors less than R+1 bits. Let's look at this CRC. How do we calculate the CRC? Is simply the binary division. So we have the data bits. Remember, guys, this is our data bits 10111100, and this is our generator. We are trying to divide by this D to the G, binary division. So this is the mathematical formula. Let's do it together. So we have 1011 and we have ones. 1 times 1001 is equal to this. If you add them up, is 1 plus 1, 0, 1 plus 0, and we have another 1. So it becomes 1. And this is gone. So now we end up with 101. So we keep divide this to G. So that's why we need to add one more 0. So 0 times this is equal to 0, and add them up is 1, 0, 1. So still we cannot divide, so we need another 0 from here. So is 1, 0, 1, 0, and divide. So we have just 1 and then 1001. We add them up. 0 plus 1 is 1. 1 plus 0 is 1, and so on. So you do until you for all these data bits, and the remaining is called CRC. So this is the remaining part, and we call this as a remainder as a CRC. So we add this 0, 1, 1 as a CRC bits to the frame and send along with the data bits. Okay, guys, any questions so far? Okay, so the next topic is called multiple access protocols. One of the main function that or services that is provided by this layer. And first of all, we have two types of links. We can divide into two parts. The first type of links is called point-to-point, and this is used for the dial-up access or between the Ethernet switches and hosts. And we have another type of links which is called broadcast links, and this is used in the old-fashioned Ethernet in upstream hybrid fiber and copper links, and 802.11 wireless LAN Wi-Fi. So some examples, we have a shared wire between the hosts, as you see from here, and we have a shared wireless link in case of Wi-Fi. We have a shared RF in case of satellite, like a GPS. And then, of course, this has some analogy in the human conversation, like humans at a party. They talk to each other by using the shared air. And in this case, we used, of course, the acoustic or speech signal. Okay, so our case is a single shared broadcast channel because we have usually a kind of, let's say, Wi-Fi access points or a base station. And through this broadcast channel, we need to access to the resources. So in this shared channel, there are some problems, of course. The first problem is if two hosts try to access simultaneously, we may have some interference, which we call collision. So when the collision happens, if a node receives two or more signals at the same time, right? So there are two mobile devices trying to access at the same time. At the receiver side, at the Wi-Fi access point, they may collide to each other, which is gonna create a collision. So one of the main problems in the multiple access protocol is this collision. So that's why we need a kind of multiple access protocol so that we can manage to provide that service to the multiple hosts without this interference or the collisions. That's why people, they develop a different types of multiple access protocols. In all of these multiple access protocols, the main idea is to come up with a distributed algorithm that determines how the hosts share the channel and determine when and which node is going to transmit. They put in some order in time, frequency, and so on, so that we can avoid these collisions. And the communication about the channel sharing also must use the channel itself. So in practice, we don't use any kind of out-of-band channel for this coordination. We use the same channel in practice. Okay, before going to the practical multiple access protocol, let's give the idealistic case assume that we have the broadcast channel of rate r bit per second. What is desired in this case is when one node wants to transmit, it can send at a rate r. So if there is only one node that is trying to transmit its datagram or packets, it can send and it can utilize the whole bandwidth, right, r, because there's no other node. But in practice, you know, there may be m number of nodes that want to transmit, and each can send at average rate of r over m, of course. And this can be fully decentralized. So in such case, there's no special node to coordinate this transmission and no synchronization of clocks or slots. This is a simple version, an idealistic version. But when it comes to the practice, we have a different conditions. So that's why we are gonna divide the MAC protocols under 3 categories. The first category is called channel partitioning methods. The second one is called random access methods. And the third one is called taking turns methods. So let's look at the first, channel partitioning. In this approach, we divide the broadcast channel into smaller pieces, and we can split this in the time, in frequency, in code, and in different domain. And we allocate each of these pieces to a specific node for exclusive use. So that approach is called channel partitioning. In the random access, we say, okay, we are not going to divide the channel, but so that everyone can access anytime to this channel. But this will allow collisions, of course, right? Because there is no any kind of arrangement. And we need to come up with some method to recover from the collisions. So the collision is not avoidable. So it's part of the this approach. So that's why we need to come up with a solution that can recover from these collisions. And the third one is the taking turns. So you know, the nodes take the turns, but the nodes have a more packet to send, can take longer turns. So it depends on the packet size that you have. Okay, these are the main 3 approaches that we use for the multiple access protocols. Let's look at the details of each of these approaches, starting with the channel partitioning. And in channel partitioning, we have different methods. The first one is called TDMA. TDMA stands for time division multiple access. So as the name implies, the host nodes access to the channel in rounds. So each station gets fixed length slot in each round. If these slots are not used, they go idle. Let's give an example. We have a 6 slot frame. 1, 2, 3, 4, 5, 6. And in this case, this is the first round, this is the second round. In this case, we have 1, 3, 4 packets that are used, and the remaining 2, 5, 6 slots are idle, not used, right? So the first node is gonna transmit within this time slot, and then it's gonna wait for the second nodes, third nodes, fourth nodes, and so on. And as you see, the blue one, the number of one node, it has to wait for the other second round so that it can retransmit. So that's one of the main disadvantages of this approach. You just can transmit within the time slot that is allocated to you. And then you have to wait for the others, like in this case is the 6th node. And after that, in the second round, you can transmit only within your time slot that is allocated to you. So there's a kind of delay that you need to tolerate in this case. Another approach is called FDMA, which stands for frequency division multiple access. So we split the channel. In the previous case, we split the channel in the time domain. In this case, we split the channel in the frequency domain. So we give a sub-channel. Each station or nodes is assigned a fixed frequency band. So in this case also, let's say this is the 10 megahertz channel, and I have 1, 2, 3, 4, 5, 6, let's say 12 megahertz channel, and I have 6 sub-channel. So I divide it into 6 sub-channel, 6 pieces. So that means each of them is gonna be 2 megahertz. So one node, like a blue node, can always utilize this 2 megahertz channel without waiting the others in the previous case, in case of TDMA. So that's the main advantage of FDMA over the TDMA. So the nodes do not have to wait the others. All of them can, simultaneously utilize their sub-channels. But the disadvantages compared to the TDMA, in case of TDMA, you have to wait your turn. When your time comes, you can utilize the whole 12 megahertz, the whole channel. But in this case, you don't have to wait, but when you always can utilize only 2 megahertz, which is 6 times less than the TDMA case. So there's a trade-off. It depends on your application. You can select either FDMA or TDMA by considering these pros and cons of FDMA as well as the TDMA. Okay, the second approach, we call it random access protocols. We are not going to allocate exclusively a channel or time slot to a node. It's open to everyone. So one node has a packet to send, it transmit at full channel data rate. And there's no any kind of prior coordination among the nodes. But the problem is there's no rule. Everybody can transmit at the same time to access to this channel. But in such case, we may end up with the collision, right? If 2 or more transmitting nodes try to send the packet at the same time, we may end up with the collision. So that's why the random access protocols need to address the following issues: how to detect the collisions, and then after detection, how to recover from these collisions. Some of the popular methods of random access protocols are slotted Aloha, CSMA, and their version, which is the collision detection and collision avoidance version. CSMA is carrier sense multiple access. And let's look at all these 3 different random access protocols together. By starting with the simple one, is called slotted Aloha. So in this protocol, we assume that all the frames have the same size and the time divided into equal size time slot. So in each slot, we transmit 1 frame, and nodes can start to transmit only at the slot beginning. And we also assume that the nodes are synchronized. If 2 or more nodes transmit in a slot, all nodes detect the collision. So based on these assumptions, Let's look at the operation of these protocols. When node obtains fresh frame, it transmits in the next slot. If no collision happens, node can send a new frame in the next slot. But if you experience a collision, node, because collision happens, your packet is lost, the node retransmit frame in each subsequent slot, of course with some probability, let's call it P, until it successfully transmit this frame. Look at visually how this works by giving an example. Assume that I have a 3 node in the network, and these 3 nodes wants to send their frame, right? So in the first slot, all 3 attempt to send their frames. Because we have only one channel, there's no coordination, and then if all 3 tries to send at the same time, the collision is going to happen, which we call C, collision. So once all the nodes detect this collision, all the nodes step back, wait for a slot, as you see. So collision happens, and we detect the collision. That's why all the nodes step back. And then the next slot, it becomes empty. No one sent any frame, so it wasted. So some of the nodes kind of either conservative, so that's why, let's say in this case the node 3 is conservative, only 2 nodes attempts to resend in the 3rd slot. And again, as you see, the node 1 and node 2 collide to each other. So they detect the collision, and these 2 step back again. In the 4th slot, so let's say node 1 is conservative, only node 2 sent its frame, and successfully, that's why we call sent S. But still we have the node 1, that node 3 that haven't sent their frames yet. So that's why they wait another slot, which is empty. Now both node 1 and node 3 think that, now the channel is free, I can send. So both of them, they jump and try to send. But again, in this slot, the node 1 and node 3 collide to each other. So there's a collision. So that's why they step back, and another empty slots, they wait for some time so that the channel become clear. And we wasted another slot. Now, assume that node 1 only sent in the next slot successfully. And then after that, in the last slot, because node 3 only left, so node 3 is gonna transmit. So as you see, this is very simple. There's no coordination, there's no rule, kind of, compared to the channel partitioning. So that's why this algorithm has some pros and cons. Let's look at the pros. The first advantage is single active node can continuously transmit at full rate of channel. That's true. So once node obtains this channel, it can send a full rate. It can utilize the whole channel, whole bandwidth. And the second is highly decentralized. You don't need to kind of use any kind of resources for the coordination. There's no need for the coordination. Only slots in the nodes needs to be in sync. And it's very simple, as you see. Just attempt to try to send it until you're successful. So that's the simple strategy. Let's look at the cons and disadvantages of these protocols. As you see, only 3 nodes are available in this network. And then we have many collisions. I have 3 collision in this case. And then I have E, 3E. So 3 slots are wasting. So there are many collision and wasting slots. There are many idle slots, as you see. And the nodes may be able to detect collision in less than time to transmit packets. And it requires the clock synchronization in this case. And these are the main disadvantages of this slotted Aloha. So in terms of performance, let's measure the performance of this slotted Aloha protocol in terms of efficiency. So what's the efficiency? Is defined as the long run fraction of successful slots. So assume that we have n nodes with many frames to send, and each transmit in slot with probability of p. And how we calculate this probability that given node has success in a slot is equal to p times 1 minus p to the power of n minus 1. Probability that any node has a success is called n times the above probability. So our how to determine the maximum efficiency, we need to find the probability that maximize this probability of success. If you calculate this, and you'll see that maximum efficiency is 37%. So what this efficiency means, you are using the channel for useful transmission only 37% of time. So the remaining 63% of time, your channel is wasted, which is low. So let's look at the second type of Aloha, which is called unslotted or pure Aloha. It's simpler compared to the slotted, no synchronization. So how it works is very simple. When frame first arrives, transmit immediately. So there's no any kind of slot in this, because in the previous case you have to wait and you have to transmit at the beginning of each slot. But in this protocol, there's no slot concept. So whenever it comes, transmit immediately. And in such case, the collision probability increases, right? Because this red one is the previous frame, and this purple one is next one, and then you transmit in the middle, right? So there's a probability that you can overlap with the previous or as well as the next one. So that's why in these protocols, the collision probability is more than the previous one. Let's look at the efficiency of these protocols. Probability of success by given node is equal to probability of node transmit times and the collision with the previous and the next one. So after all this mathematical calculation, and then you end up with the 18%, which is almost half of the previous, which was 37%, right? Even worse than the slotted Aloha. So the efficiency is about 18%, the other was what, 37%, almost half of the slotted Aloha. Because the collision of probability of collision increases. But there's an advantage. It's a very simpler, no synchronization. So that's why it's simpler, but the performance-wise is worse than slotted Aloha. Okay, the last random access protocol is called Carrier Sense Multiple Access, CSMA. So in this case, the principle is very simple. You're going to listen the channel because there's only single channel, shared channel. As a node, you listen to the channel. If channel is idle, you transmit your entire frame. If channel is busy, then you defer, you delay your transmission. And it's similar. We do the same thing in the human conservation, right? Conversation. If two people, they talk to each other, we don't interrupt others, right? We just wait so that they can complete their talk, and then once they finish, if there's no noise or speech on the environment, then if the channel is idle, then we start to talk to the other person. Similar analogy. Okay, still, of course, collusion happens in this CSMA as well. Because there are some propagation delay, means two nodes may not hear each other's transmission. And then entire packet transmission time wasted when this collusion happens. So in this case, in CSMA, the distance and the propagation delay play an important role for determining the collusion probability. Let's look at an example. So we have 4 nodes in this network. The second one, and this is the 1, 2, 3, 4. At T0, the second one is trying to access the channel or sending a packet. And after sometimes at T1, the 4th node is transmitting its packets. Because of the distance between these 2 and the 4th node, they don't hear each other until this, right? Here, the 4th is gonna hear the second one, and the second one will hear the 4th one at this time. So that's why different versions of CSMA are developed. One of the versions is called CSMA CD. CD stands for collusion detection and carrier sensing, and it has a deferral as in CSMA. So this version of CSMA has an additional feature that can detect the collusions. So the collusions detected within short time. And once you detect this collusion, you're gonna stop this colliding transmission so that we can reduce the channel wastage. But this collusion detection, it can be easy in wired LANs because you can measure the signal strengths, compare the transmitted and received signals, but it's very difficult in the wireless local area networks. So this is in analogy to the human analogy, is kind of a polite talking person. So a polite person, first assume that you are a polite person. There are 2 people, they are talking to each other, and you are 2 person and for each other, and you want to talk to the same person. So, and both of you start to talk to this guy, and when you hear the other is talking, you are polite, so you stop because you detect this collusion, and then you said, you talk to him, so I'll step back. Once you're done, I'll talk to him. So how this collusion detection happen in the previous example? So the second node transmit signal packet, and then it reached to the fourth node. So, and then these guys can detect the collusion. and it start to abort its transmission because it heard that there's a collision. And similarly, the second node can detect the fourth signal at this time, so and it determine that there is a collision, so it's immediately abort the transmission so that it can avoid the channel wastage. So this CSMA CD algorithm is used in the Ethernet that you guys using at your home or offices. How this Ethernet CSMA CD algorithm works in the following steps. In the first steps, the NIC, remember that was a network interface card. It receives the datagram from the network layer and it encapsulates and then it creates the frame. So if NIC senses now we are ready to transmit, but the NIC is gonna listen to the channel. If NIC senses channel as an idle, it starts frame transmission. But if the NIC senses the channel is busy, then it waits until the channel becomes idle, then transmits. So assume that the channel is now idle. So if the NIC transmits entire frame without detecting any collision, NIC is done with the frame. But if NIC transmit and detects another transmission, while transmitting, it detects the collision basically. It aborts immediately and sends a jump signal. So this is another feature, sending a jump signal. So it detects the collision and stop its transmission, and also tells the other nodes in the network that there is a collision, there is a jump. So it broadcasts this jump signal so that the other nodes in the environment, in the network, knows that there is such collision. After aborting, the NIC need to wait for some times. But the question is how much time that the NIC needs to wait is based on the binary backoff. So it enters to the binary backoff step. So after the amped collision, NIC chooses K at random from kind of a random number, and it selects this K random number and it multiplies with 512 bits times. So it randomly select a number, so times the 512 bit times. So the NIC is gonna wait for that time. It's a kind of random time. After that, counter finished, completed, it returns to the step 2, which is here. Start to sense the channel again. So that's how the Ethernet CSMA CD algorithm works. Let's look at the efficiency of CSMA CD. So how do we calculate? Is equal to 1/1 plus 5 times T propagation over T transmission. T propagation, remember, is the maximum propagation delay between two nodes in the local area network. T transmission is to time to transmit maximum size frame. Okay, let's look at this efficiency. Efficiency goes to 1 under what condition? If T propagation goes to 0, right? If this T propagation becomes 0, efficiency goes to 1, means it goes to 100%. So you are utilizing the channel 100% time. And another condition, if T transmission goes to infinity, so you are allowed to transmit a large number of frames. In such case also, the efficiency goes to 100%. If you compare the CSMA to the Aloha, remember in the previous Aloha, it's better performance than Aloha, simple, cheap, and decentralized. That's why it becomes more popular compared to the Aloha. It's been used in many technologies such as Ethernet, Wi-Fi, ATM, and so on. Taking turns, the last approach in the multiple access protocols. So remember, in the first approach in channel partitioning, we share the channel efficiently and fairly at high load. So you have a channel, you split this channel into the small pieces in the time domain or frequency domain. At the high load, this approach is efficient and fair, but inefficient at low load. If you have a small number of nodes in the network, it's not efficient way to use, because delay in channel access, interference over the noise bandwidth allocated, even 1 over n bandwidth allocated, even if only one active node. And for the remaining time slots or the frequency, sub-channels are not utilized. So in summary, channel partitioning is efficient and fair when you have a large number of nodes or high network load, but is not efficient at the low load. Random access protocols, its opposite way, is efficient at the low load when you have a small number of nodes, so that node can fully utilize the channel. But when you have a large number of nodes in the network, they are trying to access to a single share channel. Of course, at the high load condition, there may be a lot of collisions, which is gonna degrade your performance. So taking turns is kind of a combination of these two channel partitioning and the random access protocols. It takes the advantage of both approaches. Let's look at how it works. We have two methods that we're going to discuss in this approach. The first one is called polling. How this polling works, we have a master node and we have slaves nodes. So the master node is going to invite slave nodes to transmit in turn. So master node, it invites. So it's kind of an arrangement, and typically used with dumb slave devices. And the concern in this approach is that the polling overhead, so because the master needs to invite and wait for the response and so on. So that's why the latency is another issue, and more important is a single point of failure. Everything is dependent on the master's node. If something happened to the master node, the network will, down. Let's look at the animation. So invites the first one and send the data, invites the third one, the third node send the data. And another method in taking turns approach is called token passing. So the control, we have a token, which is control if you're a node, this token is always in the loop, is moving around the loop. So if you have a packet to send, so you take this token, and once you are done, you are gonna release your token to the loop again. The main concern in this method is because the token overhead, you have to wait and for this, which is going to introduce additional latency. And also we have a single point of failure in this case. When something happens to the token, the network will shut down. So let's look at the animation. Nothing to send. This node doesn't have anything to send, so that's why it doesn't keep it passed to the next one. This node has some data blue, as you see. It capture the token. It transmit its data, Once it's finished, it releases the token. And some other like cable access network that you use for your home internet or cable TV system. So we have a downstream, we have an upstream. At the downstream, we transmit internet frames, TV channels, control using at different frequencies. In the upstream from your home to the center, ISP center, at different frequency in time slot, we transmit the internet frames, TV control, and so on. So multiple 40 megabit per second downstream channel, multiple 30 megabit per second upstream channel. So in this case, what kind of multiple access we use? In this case, all the users content for certain upstream channel time slots. Another one is called DOCSIS, Data over Cable Service Interface Bank. FDM is used over upstream, downstream frequency channels. TDM upstream, some slot assigned, some have contention, and so on. So to summarize the multiple access protocols, we have three approaches. The first one is channel partitioning. We partition or split the channels into small pieces in the time, frequency, or code domain, such as TDMA, FDMA. Random access is more dynamic. There's no coordination, but there's a collusion in this case. So different types of protocols, Aloha, slotted Aloha, CSMA, CSMA-CD. Carrier sensing is easy in some technologies and hard in the wireless, of course. CSMA-CD is used in Ethernet, CSMA-CA is used in the Wi-Fi. The third approach is taking turns which exploit the advantage of these two approaches. So pulling from central site or token passing are two popular methods in this approach. The Bluetooth FDDI token ring, they utilize these methods. Any question, guys?